Hi there, this is Professor Barber. I'm providing you work exercises of problems similar to some of the problems of your homework assignment. Prove the following statement. If 2 divides b, then 2 divides n times b, where n is an element of the integers. So let's begin. I'll write PF to indicate that I'm beginning my proof here, and I'll begin with the premise. 2 divides b tells us definitionally that b is equal to the product of 2 times some a, where a is an integer. Just applied the definition. Then guess what? We can multiply by n on both sides, so n times b equals n times 2a. For some n, an integer. Let's apply the commutative property to the expression on the right-hand side. So I'll write this as 2 times n times a, and I'm going to let z just take the place of the product n times a for some z that's obviously an integer. Then we get n times b equals 2 times z. Then we can apply the definition of divisibility, and it shows that 2 divides nb. Q, E, D. If d divides a and d divides b, then d divides the sum of a plus b. So let's begin this proof, and we'll apply the definition. D divides a means that a is equal to the product of d times n, where n is some integer, and d divides b means b is equal to the product of, and we'll write this as, let's see, d times m for some m. That's an integer. So let's do the addition. We know that a plus b, a is equal to d times n, b is equal to d times m. We could factor out the d, so we get d times the quantity of n plus m. And now we have that a plus b is equal to d times n plus m. By the definition of divisibility, we get then that d divides a plus b. I forgot to put instructions on here. The statement states, if 4 divides a plus b, then 4 divides a plus 4 divides b. One valid counterexample is all that is needed to disprove a statement. So I picked one. I said, consider that 4 divides 52. That's a true statement. And we know that 52 is the sum of some two numbers, so I decided to split that up into 39 plus 13. Then we know that 4 divides 52 means that 4 divides the sum of 39 and 13. However, look what happens. 4 doesn't divide 39. 4 is not a factor of 39. And furthermore, 4 also does not divide 13. So this is a false statement by the one valid counterexample. Solve the linear Diophantine equation using modular arithmetic. Describe the general solutions. Diophantine equations is basically doing modulo arithmetic and looking for a common remainder. Before I proceed, I'm going to see if the equation 6x plus 10y equals 32 can be simplified a little bit. So I'm going to begin with asking the question, does the greatest common divisor of 6 and 10, those are the coefficients from the left-hand side, divide 32? Well, the greatest common divisor of 6 and 10 is 2. That's 2 divides 6 and 2 divides 10. And does 2 divide 32? Yes, it does. So let's simplify the 6x plus 10y by factoring out or dividing out that one common term, and we'll have 3x plus 5y equals 16. That is 6x plus 10y equals 32, and 3x plus 5y equals 16 are equivalent. Now I'm going to look at the factors that are the constants multiplied to the x and to the y, and I'm going to start with 3 because that's a lesser number. You can do 3 or 5, but as a general rule, the smaller number is better. And I will rewrite this using modulo arithmetic. So 3x plus 5y is congruent to 6 mod 3. Now, if we divide by 3, we're going to list the remainders. 3 divided by 3, the remainder is 0. Plus 5 divided by 3, the remainder is 2. So we got 2y. And 16 divided by 3. Okay, so 3 goes in there 5 times, so 16 minus 15, the remainder is 1, so that's congruent to 1, mod 3. So continuing, I will have 2y equals 1 mod 3. So if we take that remainder and we were to add the 3 to the number on the right hand side, could we get a multiple that is divisible by 2? And the answer is yes. That is, if we add 3, we can write 2y is congruent to 1 plus 3, which is 4 mod 3. The remainder remains the same, right? Because we're just adding that remainder. And dividing by 2 on both sides, get y equals, or y is congruent to 2 mod 3. Now we can rewrite this in solving for y as an equation, and you get y is equal to 2 plus some multiple of the remainder, 3, for any k that's an integer. Now let's solve for the x in the simplified form. So I'm going to use the simplified form, and I'll have 3x plus 5, and the y that we just solved for is 2 plus 3x, and that'll be equal to 16. Let's simplify some more. I get 3x plus 10, and I'm just going to write this as 5 times 3 times k equals 16. Let's get the x by itself. So 3x is equal to 16 minus 10 gives me 6 minus, then I'll have 5 times 3 times k. And then I will divide by 3 all the way through. So I get x is equal to 6 divided by 3 is 2, minus 5 times 3 divided by 3 is just 5k. And so my Diophantine equations, the general solutions are x equals 2 minus 5k, and y equals 2 plus 3k. I encourage you to plug those in and make sure that you get the right answer.